Hi, this is the first lecture in frequency response of continuous time linear time invariant system. Okay, let's assume that we have a linear time invariant system and the input is x of t and the output y of t. And the impulse response of the system is h of t. Now, what is the relationship between the output and input? Or how can you get the output? We know that we can get the output if we use convolution. So we can say that y of t is equal to h of t conjugated on, the input x of t. And we learn how to do that using integration. And it's kind of a hassle. But if you have linear time invariant system and you know about Fourier transform, you can do it easily by transforming everything using Fourier transform. So your equation there will be y of omega is equal h of omega times, not conjugate times, it will be turned to multiplication of omega, which will be easier mathematically to deal with. And you can find the relationship between the output and input by h of omega. The impulse response in frequency domain will be equal the output in frequency domain divided by the input of in frequency domain. And this h omega, in general, it's a complex. It has real and imaginary. So it has a magnitude and an angle. So you can express it as a magnitude and angle. Okay, so and that will and then we can sketch the change of the magnitude with the frequency omega. That's the magnitude, which is equal the magnitude of the impulse response. And also you can sketch the phase of the impulse response with omega. And that's very important relationship. So you can know the effect of this system on the input magnitude and phase. Great. Let's take a simple system and see how can we solve it. How can we implement the theory with it? Let's assume that we have a linear time invariant system and its impulse response in frequency domain is equal to 1 over 1 plus j omega. That will tell you about the relationship between the output and input. Now let's find the magnitude. The magnitude of the impulse response in frequency domain, you just find the absolute value of it, which will be equal 1 over the square root of 1 square plus omega square. So you have 1 over 1 plus omega square. That is the magnitude of the impulse response. What about the phase? The phase theta will be equal the angle of the top minus the angle of the bottom. And since you have 1 in the top here, so the angle is equal 0 degree. Minus the angle on the bottom, which is equal to 10 minus 1, the imaginary part divided by the real part. When you are using this equation and omega giving there, it will be in radian. So everything should be in radian. So not to mistaken, I'm not going to say right here degree, but I'm going to write radian. And the angle here is radian, that's the total. And if you want to change it from radian to degree, you just multiply the whole thing. You can multiply it by 180 divided by pi. So that's the magnitude and the angle. Let's do in this example. Now the magnitude is changing with the frequency according to this equation. M is equal to 1 over 1 plus omega square. Let's study this relationship over frequency from minus 10 hertz to 10 hertz. we'll say we'll start from minus 10 up to 10, and let's say that the step will be 0.1. To do that, I'm doing this in MATLAB. And then you can find the frequency omega by multiplying the frequency by 2 pi, because we know that omega is equal to by f. So you can write it's equal to 2 times pi times omega and times f. And you can find the magnitude by write the relationship, say m is equal 1, and then divided by 1 plus omega squared. But remember, omega is a row vector, so when you divide, it's not enough to do that. To make a division element by element, you vote before the division symbol here, a dot. Square root, because if you want to find the square root, as we did here, so you write square root 1 plus omega squared. You multiply omega times omega. It's not enough to multiply omega and omega like that, because it's element by element. You put dot before the multiplication. And so what you did now, you just coding this magnitude 1 over the square root of 1 plus omega squared. So what's left is just, you wanna sketch it. But let's also look at the effect on the phase. Let's call the phase in the program, I will call it in the MATLAB P. So I will write the formula for the phase. P is equal to minus A tan and omega over 1, or just omega. That will give you the phase. And now you can sketch it by writing the command subplot, because you are going to divide your screen into 2 rows, 1 column, and the first screen you make plot to the magnitude against the frequency omega, and that's here we have the magnitude is done. And then your second window, you are going to write subplot to 1, and the second screen you are going to plot the phase against them, and then you sketch it. Well, when we did that, I will give you the result, and you should try to run the program and write the code. And I found that at 0 frequency, when omega is equal 0 radian, we found that the magnitude here of m is equal 1, and then decrease with increasing the frequency. So that's the magnitude we get from MATLAB. You got to understand what does it mean, this magnitude. It means if you have an input to the system that we just explained here, the linear time invariant system, if you have omega equals 0, it means if you have a DC, so the magnitude will not be affected, will be preserved, because the m is equal 1, it means the magnitude of the output is equal 1 times the magnitude of the input. So it will keep it. But every time you are increasing the frequency, what's happening here? Every time you're increasing the frequency, the magnitude m is decreasing. So if you take another value here at this omega and you go for the magnitude is less than 1. And every time you increase the omega, the magnitude is decreasing. What does it mean? It means that in the system, every time the input frequency is increasing, its magnitude will be decreasing till you go to the high frequency, and you'll find that the signal almost vanishes, almost equal 0. So it means that the system only preserves the signals that has a low frequency. So you can consider the system as a low frequency filter. It means it just allows the signals with low frequency to pass and does not allow the signal with the high frequency. And if you have a signal that it's composed of low frequency and high frequency, it will prevent the high frequency to pass. And then you study the phase shift and you sketch it. Then we found that that's the result what we got. If this is the omega and we are sketching the phase theta and I convert it to degree. You convert it to degree. I mean, if you wanna, when you sketch with the degree, if you leave it like that, it would be in radian. But if you wanna convert it to degree, so the whole thing you got to multiply it by. So let me just modify it for you. You multiply it by 180 divided by pi. So your angle now will be in degree if you want to have a sense of it. If you sketch it, I will give you just approximation. You'll find that when omega is equal to 0, there is no change happen, and every time that you are increasing omega, this shift is increasing, but in the end will be like almost constant after a certain value of omega. Okay, so and you can calculate it, by using this equation of the equation, as you know, theta is equal minus 10 minus 1 omega. So when you have 0 here in omega, so 10 minus 1, 0 is equal 0. It means it does not make any shift of the signal when it's DC, because DC doesn't have any shift. All right, and every time you're increasing the omega, the theta is increasing by negative because you have minus sign here. For example, when you have, let's say that the phase is equal 1. So when you reach omega is equal 1, what is the phase shift? Will be minus 45 degree. So it's going like that. Okay, so it will continue like that. Let's say that you are getting a high number. What does it mean, high number? What is the angle? Its cosine is almost 0. So it's like it's getting closer to minus pi over 2 or minus 90. When you go to the other side of the omega, you'll find it's very symmetric, the same thing, and then we'll go to plus 90 degree. So the maximum that will make shift at high frequency to minus degree. So that, what does it mean when you make frequency response of continuous time linear time invariant system? And you will find in the handout that the same analysis done for very similar system. Second video, we are going to continue to explain the relationship between the input and output and how find the output.